guys, so today we're going to be talking about linear functions. We will start with the definition. So a linear function is a function whose graph is a non-vertical line. So we can think of this just like a linear equation. We already learned the definition for that, but a vertical line will not be included in this because of course a vertical line would not pass the vertical line test. So a vertical line would not be a function. So a linear function, to define that, is just a function whose graph is a non-vertical line. It can be written in the form y equals mx plus b, just like a linear equation. And m is our slope and b is our y-intercept. Now, much of the examples that I'm going to go over are not going to really be new to you. We're kind of just using our new function terms and terminology, vocabulary. But a lot of this is going to seem very familiar and relates to a lot of what we learned in our chapter on linear equations. So example 1 says, use the graph to write a linear function that relates y to x. Okay, so when we are writing a linear function, that is another way of writing a linear equation, right? It can be in the form y equals mx plus b, except it will not be a vertical line. We're relating y to x, and we have some points here on our graph. So I need to use these points to come up with a equation, y equals mx plus b, where m is my slope and b is my y-intercept. Now to find slope, there's a couple of different ways I can go about this. I can make a slope triangle between 2 points, or I could make a table of values, or I can use my slope formula. So I'm going to make a slope triangle for this example. You can see that we are going up 1, 2, 3. That is my change in y, and we are going over 2. That is my change in x. So slope for this would be 3 over 2. Y equals 3 over 2x, and now I need to find my y-intercept, which I can see is already clearly labeled on the graph for me. When y is a point, when we have a point on this y-axis, the x value is 0, and the y value is our y-intercept. So we have -3. The equation, or the linear function that relates y to x, is y equals 3/2 x minus 3. Okay, so this is the same process we used when writing a linear equation from a graph. We're just defining it as a linear function now that we understand that a function is when each input has exactly one output. Moving on to example 2. We're going to use the table this time to write a linear function that relates y to x. All right, so we have this table here. After I make the table, I'm also going to show you how we can go about graphing this. So in this example, I am going to, instead of using a slope triangle, I am going to find the slope using my slope formula. So just a reminder of slope-intercept form, y equals mx plus b, where m is the slope and b is the y-intercept. My slope formula is the change in y values over the change in x values, okay? So I'm just going to choose 2 points here and use my slope formula to find the slope for this equation. I'm going to do change in y first, so 9 minus 7 over change in x, -3 minus -2. 9 minus 7 is 2. Remember that subtracting a negative is the same as adding a positive. -3 plus 2 is -1, and my slope is 2 over -1, which equals -2. Now to write my equation, I'm also going to need to find my y-intercept, which again is already given to me as one of the points. My y-intercept is whatever y is when x equals 0. So in this case, when x equals 0, y is 3. So my y-intercept is 3. Now that I know what both m and b are equal to, I am going to just plug them into my slope-intercept form equation. So y equals negative 2x plus 3. And if you were to graph this, instead of using the slope formula, you may have graphed this and found the slope by making a slope triangle like we did in example 1. So I would just be graphing each of these as points. My first point would be at negative 3, 9. Negative 3, 9, it's right about here. Negative 2, 7 is right about here. Negative 1, 5 is here. And 0, 3, and those are the points. Okay, so that is how I could use this table to graph, and then I could have found slope by making a slope triangle, and I would have said, all right, I went up 1, 2, and then to the left 1. So I would get the same slope of 2 over negative 1 or just negative 2. All right. Next, we have a real-life application of this. So it says you are controlling an unmanned aerial vehicle for surveillance. The table shows the height y in thousands of feet of the UAV X minutes after you start its descent from cruising altitude. Okay, so we have an unmanned aerial vehicle. Think of that as like a drone that is descending. It says it's starting its descent from a cruising altitude. Now, part A wants us to write a linear function that relates y to x. We are going to interpret the slope and the y-intercept. So there's that word interpret. Remember, the word interpret means that we are putting the slope and the y-intercept numbers into real-world context. All right, so let's come up with the linear function first. Again, we have slope-intercept form, y equals mx plus b, where m is the slope and b is the y-intercept. All right, let's find our slope first. It would be change in y over change in x. So I'm going to use my slope formula again. I'm going to take two values from this table, 65 minus 60 over, and then I have 0 minus 10, which is going to give me 5 over negative 10, which when I simplify is negative 1/2. I have found my slope. The next step is to find my y-intercept, which once again is given to us in the table. My y-intercept is just whatever my y value is when x is 0. In this case, it is 65. And I can use that to write my equation. Y equals negative 1/2 x plus 65. And the last thing I want to do here, let's not forget, is that we are interpreting the slope and interpreting the y-intercept. All right, so I'm going to write an interpretation for each of these. My slope is negative 1 over 2. To interpret that, I need to add units. That's going to add some real-world context to this, right? So this top number was my change in y. Y represents height in thousands of feet. Okay, so this would be negative 1,000 feet over, and then x represented, my bottom number is x, change in minutes. So my interpretation of slope would be that we were descending. Remember, there's that negative sign. That means going down in this situation. The UAV descended 1,000 feet, because that was in thousands of feet, every 2 minutes. And then I would interpret the y-intercept, and I could interpret that by saying at 0 minutes, the UAV was at 65,000 feet. Or to make it a little more clear, if you wanted to say instead of at 0 minutes, you could say before the descent began, okay? Because at 0 minutes, it's before the UAV has descended at all. So you could say before the descent began, the UAV was at 65,000 feet. You could say at the start of the descent, the UAV was at 65,000 feet. Those would all be acceptable as well. And now in part B, we want to graph this linear function. Okay, so we're just taking all of the skills that we've previously learned and applying them to some real life problems here. So I have the equation already written. I have a table of points as well. I am now going to graph this. So the first point I'll put at 0.65. It's right about here. Next we have 10.60. Next we have 20.55. And last we have 30.50. Excuse me. All right, so I graphed the points. Now, in this situation, I need to decide, am I going to connect these points with a line or not? And I need to think about the context of the situation to make that decision. All right, so in this case, when I'm graphing the linear function, on my y-axis, I have height in thousands of feet, and on my x-axis, I have minutes. I need to determine, would it make sense for there to be a height somewhere between 0 and 10 minutes? And in this case, I would say yes, of course. It's still descending between that 0 minute mark and that 10-minute mark, and it's going to be at a certain height. So it makes sense for me to connect these points with a line, although it would not make sense for me to go into a negative quadrant, right? Because we are not going to have negative time here. So I'm just going to connect them with a line. It's not perfect. And then draw my little arrow showing the descent. And that is our graph. And we have one more part to this. In part C, we are asked to find the height of the UAV when you stop the descent after 1 hour. Okay, so after 1 hour, that would be 60 minutes, right? 1 hour equals 60 minutes. So we're trying to figure out the height of the UAV after 1 hour, or in other words, after 60 minutes. We have the equation, which I'm going to rewrite. It's y equals -1/2 x plus 65. All right, and I'm going to use that equation to find the height after 60 minutes. Just a reminder that the x represents minutes and the y represents height. So I'm looking for y because I'm trying to find the height, and I'm given x because I know the amount of minutes. It's 60. So I'm going to plug this number 60 in for x. We're going to use substitution to find the height. Y equals -1/2 times 60 plus 65. And I will multiply first. -1/2 times 60 is 30 plus, -30 plus 65. And we get y equals 35. Now remember that height is in thousands of feet, so I would say after 60 minutes or after 1 hour, the UAV is at 35,000 feet. And that's it. We have one more example here, and this is an example where we are actually going to be comparing two different linear functions that are given to us in two different formats. So you'll see in this problem, we have a table to represent one linear function, and we have an equation to represent the other linear function. And we're going to figure out how can we compare these two things that are written in different formats. So it says the earnings Y in dollars of a nighttime employee working X hours are represented by the linear function y equals 7.5x plus 30. The table shows the earnings of a daytime employee. Okay, so we know a nighttime employee follows the equation y equals 7.5x plus 30. And the daytime employee, we don't have a linear function equation written. We just have this table of values for the daytime employee. Now it wants to know which employee has a higher hourly wage. So to figure that out, we need to look at what both y and x represent. Y is representing their total earnings in dollars, and x is representing time. Now, something we all already know is that when you have a job, to figure out how much you're making per hour, you need to know how many hours you worked, right? You're going to multiply the amount that you make per hour by how many hours you work, and that is going to give you how much you made for the day. So it makes sense that the number we are multiplying by the amount of time we worked would be our hourly wage, okay? So in this one, we can simply look and say the nighttime employee must make $6.50 per hour, because that is the number that you would multiply by X, or by their total number of hours, right? Now the daytime employee, for this one, we need to look at the table that we were given. This one, we can see that the X values are going up by 1 or 1 hour, and the Y values are going up by $12.50 or $12.50. So it's pretty clear just from looking at this table that the daytime employee is making $12.50 per 1 hour. Okay, so from here, I can answer this question, which employee has the higher hourly wage? And I would say it is the daytime employee. Now in part B, it asks us to write a linear function that relates the daytime employee's earnings to the number of hours they worked. All right, so I am taking the information from this table, just like I did in the previous examples, and I am going to write a linear function. So remember, it is in the format y equals mx plus b. And I already know my slope, or my m, is their hourly wage, which we already figured out is $12.50 an hour. So I can say 12.5x. And then I just need to take a look to see if there is an initial value. All right, so if I take a look at this table, I can follow this pattern backwards as well. The x values were going up 1 each time. I want to find out what is y when x is 0. Okay, that is what the y-intercept is. It's whatever y is when x is 0. So I go back 1, I follow the pattern backwards, and then I need to follow the pattern backwards on the bottom as well. So instead of plus 1250, I'm going to say minus 1250. And if I do 1250 minus 1250, I get 0. That right there tells me that the y-intercept is 0. I don't need to write that plus 0 at the end. I can just leave this as y equals 12.5x. All right, there is another part to this. It says, in the same coordinate plane, graph the linear functions that represent the earnings of the two employees and interpret the graphs. Okay, so these are already graphed to the side here. We see the graph for the nighttime employee and the graph for the daytime employee. All right, so these are both of the equations that we wrote on the same graph together. Now we're going to take a look at this and interpret the graphs. There's that word interpret again. So explain what these graphs show in real world context. Okay, so I might say something like the nighttime employee makes more money overall, because we can see the earnings are over here. And this graph is higher for earnings. This is the graph of the nighttime employee. So the nighttime employee is making more money. They have higher earnings overall than the daytime employee until this point here, right? So the nighttime employee makes more money overall until they have both worked for how long? I can see that this point falls at 6 hours. Until they have both worked for 6 hours. At 6 hours, they make the same amount. And then after 6 hours, the daytime employee is actually earning more overall. Okay, so that might be my interpretation of this graph. Now, these are just a couple of examples. As you can see, this is a lot of what we have seen previously in other chapters. We're just connecting all of these things and figuring out a way how to compare them as well. So it's not a ton of new material for this chapter. It's just making connections to the past chapters that we have already looked at. I hope you guys have a great day. If you have any questions, make sure you contact your teacher.